Let's take a look at the concept behind the center of mass. In order to understand center of mass in 3 dimensions, we first have to draw all the way back to 1 dimension. And so this is action happening along a line where we have a mass placed at one point on the left, another mass placed at another point on the right, and we're trying to find where will we be able to place a fulcrum to balance this out. Archimedes' law of the lever says the following, that the rod will balance when you multiply the mass times the distance and get the same value on the left as on the right. And so now let's take this and place this on the x-axis, on the positive part of the x-axis. So we have mass 1 on the left, mass 2 on the right. And we're trying to find out, where's this center place at? Where's this fulcrum at? Where do we place the fulcrum in order to get a balance? We call that place x bar. Okay, now 0's over here, so in order to get this distance d1, we subtract x1 from x bar. X bar minus x1 will give you this distance that represents how far the first mass is, how far mass 1 is from the balancing point. Then we take x2, the longer distance, and subtract x bar, and that'll get you how far the mass m2 is from the center point. Alright, great. Well, from above, from Archimedes, we understand then if we multiply our mass times our distance, it should be the same on both sides. So mass 1 times d1 should be equal to mass 2 times d2 in order to get the balance, where we use d1 replaced by x bar minus x1 and d2 replaced by x2 minus x bar. Okay, we'll go ahead and FOIL this out. Well, not FOIL, we'll just distribute the masses across. We get m1 times x bar minus m1 times x1, m2 times x2 minus m2 times x bar. We'll get the x bars on the same side by adding this over, and then we get this term here, adding that over. Factor out the x bar, you end up with m1 plus m2, and then on the right hand side, you end up with m1 x1 and m2 x2. All right, great. According to the rod will balance if this is true. Our job is to be able to find this x bar, and now we have a formula for it. We'll divide by this m1 plus m2, and we have a formula to help us find it when we have a 2-point mass, 2-point masses. We take m1 times x1 and m2 times x2, add those together, and divide by m1 plus m2. All right. m1 times x1 is the moment of the first mass. m2 times x2 is the moment of the second mass. Together, they give you the moment of the system, about the origin. The likelihood of the system to rotate about the origin. And the denominator is the sum of the two masses. The denominator is m1 plus m2. We'll call that the total mass. In general, to get this x bar, you're going to take the moment of the system and divide it by the total mass. Okay, great. This is when you have 2 points. If you have more points, then you just continue to add to the numerator and to the denominator. In general, if you have n point masses on a line, this is still on 1D, then we can add up the mi times xi as I goes from 1 to n and still divide by the total mass. And that will give us our x bar. What we're going to do is take this equation and multiply it by total mass to get an understanding of what this is saying to us physically. And so x bar times the total mass. What that is, anytime you take an x value and multiply it by a mass, that's the moment of that particular mass. And so the moment of the total mass is equal to the entire moment of the system. This numerator here is the moment of the system, the moment of the entire system. And so here's what we're saying. This place that we find, this x bar, it's what would make this statement true. X bar is where you would place the entire mass. If the total mass was concentrated at x bar, then its moment would be the same as the moment of the system, the entire moment for the system. That's what the left and right hand side being equal is saying to you. And so that's an idea of what the center of mass is. And we needed to understand it in 1D so that when we step up to 2D and 3D, we can just figure out what to do next. Okay, a moment of a system is basically the tendency of the system to rotate about. In this case, the origin. And when we jump to 2D, we'll have about an axis and so on. So anyway, this is center of mass in 1D. Now let's step up to 2D. So I have an x-axis and a y-axis. I have these points out in space, and I call the point masses M1, M2, and M3. Just 3 for this example, but there could be more. The distance that M1 is from the y-axis is called x1. You know, this point is, if I was to plot the coordinates of this point, it'd be x1 comma y1. Okay, the distance that M1 is away from the x-axis is y1. And the same for the others. So now, instead of having a moment about the origin, what we have here is a moment about each of the axes. First up, we have the moment of this particular system, the entirety of the system, the moment of the system about the y-axis. It's the tendency of the system to rotate about the y-axis. Based on the masses and how far these masses are away from the y-axis, we can calculate the moment of the system about the y-axis. We focus just on the y-axis and we do the same kind of calculation. Take the mass times the distance. M1 times x1 and M2 times x2 and M3 times x3, and add that all together, and that's the moment about the y-axis. What do we do with that? Well, we take this and then divide it by the total mass like we had done in 1D. So mass 1 and mass 2 and mass 3 all added together. And this gives us x bar, the x coordinate of the center of mass. In order to get the x coordinate of the center of mass in general, it's going to be the moment of the system about the y-axis divided by the total mass. Okay. The coordinate would be called x bar. Great. Now let's do it for the x-axis. The likelihood of the system to rotate about the x-axis. Well, that involves y's. The distance you are away from the x-axis is y. Same calculation, but instead of M1x1, we'll have M1y1, M2y2, and M3y3 all multiplied together will give you that moment about the x-axis. Divide that by the total mass, and you'll have the y coordinate of the center of mass. Okay, it's very important we get these formulas because we'll just be adding another layer on top when we jump to 3D. And then once again, like before, if we were to multiply both sides by total mass, we get this equation for the y moment and this equation for the x moment. And the interpretation of it is the following. This center of mass, x bar, y bar, is a point, okay, in space. X bar, y bar. It's a point in space where if you were to put the entire mass, total mass, at that point, it would have the same moment about each of the axes as the other, as the system has, basically. Okay, and so the likelihood to rotate about the y-axis is the moment m sub y. The likelihood to rotate about the x-axis is the moment m sub x. And so it's our balancing point. What you should picture is this thing rotated where we have the sort of view of it here, where we're sort of like a sort of side view here, and we're trying to find this place. Here's the y-axis, say, here's the x-axis. We're trying to find the place to put a fulcrum so that these will all balance out. If these were on a thin sheet of paper, where can we put this at so everything will balance out? That point is called x bar, y bar. If you add up these masses and put the entire mass there, your moments will be the same. All right, great. Now for 3D. To make these videos shorter, what we're going to do is stop at 2D.